Yes, it is correct that to set protection relays, you typically need to know the minimum value of fault current. This is because protection relays are designed to trip when the fault current exceeds a certain threshold. If the minimum fault current is too low, the relay may not trip when it should, which could result in damage to the system. The parameters listed, which are system damage curve, system short time withstand, and inrush currents, are all important considerations when setting protection relays. However, there are a few other parameters that you may also need to look at, including load current, ground fault current, and time delay. The load current is the normal operating current of the system. The protection relay should be set to trip at a current that is higher than the load current, but not so high that it trips unnecessarily. The ground fault current is the current that flows through the ground when a fault occurs. The protection relay should be set to trip at a current that is lower than the ground fault current, but not so low that it trips unnecessarily. The time delay is the amount of time that the protection relay waits before tripping. The time delay should be set to allow the system to clear the fault before the relay trips. By considering all of these parameters, you can ensure that the protection relay is set properly to protect the system from faults. Now let us delve into these parameters in more detail. First, the system damage curve. This curve represents the amount of damage that the system can withstand for a given amount of time. The protection relay should be set to trip before the system damage curve is reached. Secondly, the system short time withstand. This is the amount of time that the system can withstand a short circuit fault. The protection relay should be set to trip before the system's short time withstand is reached. Thirdly, inrush currents. These are high currents that can occur when the system is first turned on. The protection relay should be set to not trip on inrush currents, but to trip on sustained fault currents. Considering load current, it's crucial to understand its role. The load current represents the normal operating demand of the electrical system. This is the current drawn by all the connected devices and equipment under regular conditions. When setting the protection relay, one of the fundamental requirements is to ensure that the relay doesn't trip during normal operation due to the load current. To achieve this, the relay's pickup current setting must be higher than the maximum expected load current. However, setting it too high compromises sensitivity to actual fault conditions. Estimating the maximum load current involves considering various factors, including the connected load's nameplate ratings, diversity factors, and potential future expansion. Diversity factors account for the fact that not all loads operate at their maximum rated capacity simultaneously. Accurate load current estimation is a critical step in ensuring reliable protection without nuisance tripping. Now let's examine ground fault current. Ground fault current flows when an unintended path to ground develops in the electrical system. This can occur due to insulation failure, accidental contact with grounded objects, or other faults. Ground fault protection is essential for preventing equipment damage, reducing the risk of electrical shock, and minimizing fire hazards. Protection relays designed for ground fault detection are specifically configured to sense and respond to these currents. Ground fault relays are typically more sensitive than overcurrent relays, allowing them to detect even small ground fault currents. Time delay is another significant aspect. Time delay refers to the intentional delay introduced in the relay's tripping action after a fault is detected. This delay is crucial for coordinating the operation of multiple protective devices in a power system. Time delay allows downstream devices closer to the fault to trip first, isolating the faulted section and minimizing the impact on the rest of the system. Without proper time coordination, multiple relays could trip simultaneously, leading to unnecessary outages. The time delay setting must be carefully selected to balance the need for fast fault clearing with the requirement for coordination with other protective devices. This often involves using time current curves to ensure selective tripping. To reiterate, when setting protection relays, consider these parameters. First, the system damage curve defines the limits of acceptable stress on equipment. Secondly, the system short time withstand indicates how long equipment can tolerate high fault currents. Thirdly, inrush currents must be discriminated from actual fault currents. Fourthly, load current determines the minimum pickup setting. Fifthly, ground fault current requires sensitive detection. And sixthly, time delay enables coordination. Let's talk about overcurrent protection in a bit more detail. Overcurrent protection is one of the most fundamental aspects of electrical system protection. It aims to detect and interrupt excessive currents that can damage equipment or create safety hazards. Overcurrent relays are designed to respond to currents exceeding a predetermined threshold, known as the pickup current. The pickup current setting should be carefully selected to be above the normal operating current, but below the level that could cause damage. Overcurrent relays can be instantaneous or time-delayed. Instantaneous relays trip almost immediately when the current exceeds the pickup setting, providing fast fault clearing. Time-delayed relays introduce a deliberate delay before tripping, allowing for coordination with other protective devices. The time delay is typically inversely proportional to the current magnitude, meaning that higher currents result in shorter delays. Coordination of overcurrent relays involves selectively setting their pickup currents and time delays to ensure that the relay closest to the fault trips first. This minimizes the extent of the outage and prevents unnecessary tripping of upstream devices. Time current curves are used to visualize the operating characteristics of overcurrent relays and facilitate coordination studies. These curves plot the relay's tripping time as a function of the fault current. By overlapping the time current curves of multiple relays, engineers can ensure that the relays are properly coordinated. Another aspect to consider is differential protection. Differential protection is a sophisticated protection scheme that compares the current entering and leaving a protected zone, such as a transformer or generator. Under normal operating conditions, the current entering and leaving the zone should be equal. However, during a fault within the zone, a significant difference in current will occur. Differential relays are designed to detect this difference in current and trip rapidly, isolating the faulted equipment. Differential protection provides high-speed and sensitive fault detection, making it particularly suitable for protecting critical equipment. It is often used in conjunction with other protection schemes, such as overcurrent and ground fault protection, to provide comprehensive protection. Differential relays can be percentage differential or bias differential. Percentage differential relays compare the difference in current to the average current, while bias differential relays incorporate a bias current to improve stability during external faults. Now let's shift our attention to voltage protection. Voltage protection is designed to detect abnormal voltage conditions, such as undervoltage or overvoltage, that can damage equipment or disrupt operations. Undervoltage relays are used to trip equipment when the voltage drops below a predetermined level. Undervoltage can occur due to system faults, overloading, or voltage regulation problems. Tripping equipment under undervoltage conditions can prevent damage to motors and other sensitive devices. Overvoltage relays are used to trip equipment when the voltage exceeds a predetermined level. Overvoltage can occur due to lightning strikes, switching surges, or voltage regulation problems. Tripping equipment under overvoltage conditions can prevent insulation breakdown and equipment failure. Voltage relays can be instantaneous or time-delayed. Time-delayed voltage relays are often used to coordinate with other protective devices, such as overcurrent relays. Power transformers are critical components in electrical power systems responsible for stepping up or stepping down voltage levels. Transformer protection is essential for ensuring their reliable operation and preventing costly damage. Common transformer protection schemes include differential protection, overcurrent protection, and gas-actuated relays. Differential protection is the primary protection scheme for transformers, providing high-speed and sensitive fault detection. Overcurrent protection provides backup protection in case the differential protection fails to operate. Gas-actuated relays, such as Buchholz relays, detect the presence of gas in the transformer oil, which can indicate internal faults. These relays provide early warning of developing faults, allowing for timely intervention. Power system stability is a critical concern for electrical utilities. Power system stability refers to the ability of the system to maintain synchronism and voltage levels following a disturbance, such as a fault or loss of generation. Protection relays play a vital role in maintaining power system stability by quickly isolating faulted equipment and preventing cascading outages. Out-of-step relays are used to detect loss of synchronism between different parts of the power system. These relays trip generators or transmission lines to prevent further instability. Under-frequency relays are used to detect low-frequency conditions, which can indicate an imbalance between generation and load. These relays shed load to restore the frequency to normal levels. So, let's briefly review the key aspects of setting protection relays. First, understand the purpose of each type of relay. Secondly, determine the appropriate settings based on system parameters. Thirdly, coordinate the relays to ensure selective tripping. Fourthly, consider various fault conditions. Fifthly, use time-current curves for coordination studies. Sixthly, regularly test and maintain the relays. Setting protection relays is a complex and critical task that requires a thorough understanding of power system protection principles. By carefully considering all relevant factors and following best practices, engineers can ensure the reliable and safe operation of electrical power systems. Remember, safety is paramount. Always follow proper safety procedures when working with electrical equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. De-energize equipment before working on it. Verify that equipment is de-energized using a voltage tester. Work with a qualified electrician or engineer. Consider the impact of renewable energy sources. Renewable energy sources, such as solar and wind, are becoming increasingly prevalent in electrical power systems. The integration of renewable energy sources can pose challenges for protection relaying. Renewable energy sources can introduce intermittent and fluctuating generation, which can affect the performance of protection relays. The location and type of renewable energy source can also impact protection requirements. For example, distributed generation sources located close to loads may require different protection schemes than large-scale generation plants connected to the transmission grid. Adaptive protection schemes are being developed to address the challenges posed by renewable energy sources. Adaptive protection schemes automatically adjust relay settings based on system conditions. This can improve the performance of protection relays under varying generation and load conditions. The NEC, or National Electrical Code, provides guidelines and requirements for the installation and maintenance of electrical systems, including protection relaying. NEC Section 230.95 covers ground fault protection of equipment. NEC Table 310.15b16 provides ampacity ratings for conductors. It is essential to be familiar with the relevant NEC requirements when designing and installing protection relaying systems. Protection relays are essential components of electrical power systems, playing a critical role in ensuring their reliable and safe operation. By carefully considering the factors discussed and following best practices, engineers and technicians can effectively set protection relays to protect equipment, prevent hazards, and maintain system stability. Continuous learning and staying updated with the latest technologies and standards are essential for success in the field of protection relaying.